Hello, my name is Riyapal and today I'll be presenting my research titled Cryptocurrency Forecaster, that is leveraging machine learning for accurate Ethereum price prediction. The main purpose of this research was to investigate whether machine learning techniques together with technical indicators can be effectively used to predict Ethereum prices. In this project, I have analyzed historical Ethereum market data and compared multiple learning models to determine which model provides the most accurate prediction prices prices. I also investigated which technical indicators have the greatest influence on those predictions. So I'll begin with the introduction. So, cryptocurrency has become an important financial market, but one of its major characteristics is high volatility. Prices can rise or fall significantly within a relatively short period of time. This creates opportunities for investors, but at the same time, it creates major challenge predicting future price moments accurately. For this research, I selected Ethereum because it is one of the most leading cryptocurrencies and has substantial historical market data available for analysis. Instead of relying only on historical prices, my research incorporates several technical indicators. These indicators moving these include moving averages, the relative strength index, or RSI and Bollinger Bands. These indicators provide additional information about trends, momentum, and volatility in the market. The idea behind the project was, therefore, to combine these indicators with machine learning and determine whether Ethereum's closing price could be predicted accurately. So, to the aims and research questions, my research is mainly built on two questions. Like the first question, which machine learning model is the most accurate for forecasting Ethereum prices using technical indicators? So, to answer this, I have compared four models, which is random forest, gradient boosting, XGBoost, and elastic net. And coming to the second question, which technical indicator among Bollinger Bands, moving averages, and RSI has the greatest impact on model performance and Ethereum price prediction? So the first question focuses on model accuracy, whereas the second focuses on feature importance. Together, these questions allow me to understand not only which model works best, but also what information is most useful to that model. So, to the literature review, before developing the models, I reviewed previous research related to cryptocurrency price prediction. Previous studies have applied different machine learning techniques like random forest, gradient boosting, and elastic net. However, the research gap I focused on was the integration of technical indicators with machine learning models. Price alone tells us what the cryptocurrency was worth at a particular point, whereas technical indicators can provide additional information about market trends, momentum, and volatility. Therefore, this research attempts to address the gap by combining historical Ethereum market information with several technical indicators and comparing multiple machine learning algorithms under the same dataset and evaluation process. So, coming to the next, methodology and design. For the methodology, Ethereum historical data I obtained from Yahoo Finance using an API, and then I stored it in a CSV file, which is uploaded on GitHub. And the dataset covers the period from 2019 until July 2026. So in the code, the original dataset contains 2,427 7 observations and 16 columns. I first examined the data types and checked for missing values. Some technical indicators contain missing observations because indicators such as moving average require previous days of information before they can be calculated. These missing values were removed before model training. The date column was also converted into a proper date time format. I then divided the data set according to time rather than performing a random train and test split. The cutoff date was 1 June to 2025. This resulted in 1,998 training observations and 396 testing observations. This is appropriate for the study because the model learns from earlier historical information and are then evaluated on later unseen observations. The technical indicators include SMA 20, EMA 20, and RSI, as well as MACD and several Bollinger Band measurements. Then finally, I tested the four models. So, model training and evaluation. After pre-processing, I trained the machine learning model on the historical training dataset before modeling. The numerical features were standardized using standard scalar. Importantly, the scalar was fitted on the training data and then applied to the test data. I also performed hyperparameter tuning to improve the models. So the four evaluation metrics were used, which is MAE or mean absolute error, which tells us the absolute average absolute difference between actual and predicted prices. RMSE or root mean square error also measures prediction error, but penalizes larger errors more heavily for both MAE and RMSE. Lower values indicate better performance. R squared measures how well the model explains variation in Ethereum prices, where a value closer to 1 indicates a stronger fit. Finally, MAP expresses the prediction error as a percentage. So now I'll explain the code. So coming to the code, I have first imported the libraries including pandas, numpy for data manipulation, scikit-learn for machine learning, XGBoost for XGBoost model, and matplotlib and seaborn for visualization. So here I've imported the dataset directly from the CSV file, which is stored on GitHub. Then I used the df info and checked for null values, and then I removed the missing values and then converted the date variable into date time format. I've also generated a correlation heat map to show the relationship between the numerical variables, where the red darker color shows the positive relationship between the technical indicator. So as I shared that the data was split into depending on the dates and not just the train and test split. And then it was like the this was scaled using the standard scalar. Then the four models which were used were random forest. Then I calculated the values, and then the tuning was done of the random forest, which shows the graph. And we see that the predicted actual value and the predicted value 2536 and which is 2516, which is nearby but still not close. And then the gradient boosting, here we see 2536 and 2507, which is like which makes a big difference. and gradient boosting after tuning 2536 and 2505. It's still the same. And XG boost also has the same 2536 and 2553, which has a big difference. 2536 and 2523 after tuning. Still a big difference. So coming to the last model, which is Elastic Net. Elastic Net has 2536 and 2522. This is also like not too close, but as we studied, like as so the model Elastic Net polynomial degree 2 shows very closer, accurate values like 2536 and 2535, which is very close and accurate. So it is studied that the models performed Elastic Net XG, this Elastic Net polynomial degree 2 performed well, showing the values also very close. So, for example, so coming to the back to the slides, sorry. So this table summarizes the main model comparison. As shown here, elastic net with degree 2 polynomial features clearly produce the lowest errors. Its MAE was only 4.10 compared with 3651 for random forest, 3860 for gradient boosting, and 3970 for XG boost in the final comparison, which is shown here. Its RMSE was absolute, like so lower at 5.67. The most significant result is its MAPE of 13%, indicating a very small percentage error between predicted and actual values on this test data set. Therefore, this answers my first research question based on the evaluation performance in the study. Elastic Net with degree polynomial 2 features was the most accurate model among the test approaches for predicting Ethereum closing prices. So, coming to the Elastic Net price prediction, this slide provides a visual demonstration on the final Elastic Net predictions. On the graph on the left, the actual and predicted prices almost overlap across much of the test period. This means that the model was able to closely reproduce the ob- observed Ethereum closing prices in the test dataset. On the right hand, I have included examples of actual and predicted values. For example, as I showed in the code, and an actual price of approximately $2,536 was predicted as approximately to $2,535. Even towards the end of the test period on the 1st of July 2026, the actual price was approximately $1,608.96 compared with the prediction of approximately $1,607.23. These examples help demonstrate why the model achieved such low MAE, RMSE, and MAP values. So, coming to the feature importance. After determining the best model, I then addressed my second research question, which concerns the importance of the technical indicators. For the elastic net model, feature importance was determined using the magnitude of the model coefficients. The analysis identified SMA 20 or the 20-day simple moving average as the most influential predictor. So SMA 20 smooths daily price fluctuations and therefore provides information about the broader price trend. The analysis also highlighted Bollinger Bands related features among the influential predictors. These indicators provide information about the position of price relative to its recent trading range and market volatility. Therefore, based on this analysis, moving average information, particularly SMA 20, had the greatest influence in the final elastic net model, while Bollinger Band information was also important. This provides the answer to my second research question. Coming to the summary of findings. To summarize the main findings, this research demonstrated that machine learning models can be applied to historical Ethereum data together with technical indicators. Four main models were evaluated, like random forest gradient boosting, XGBoost, and ElasticNet. Among the tested configurations, ElasticNet enhanced with degree 2 polynomial features achieved the strongest performance with an MAE of 410, RMSE of 5.67, and MAPE of 0.13%. The feature analysis also showed the importance of technical indicators, particularly the 20-day simple moving average. In particular terms, this research demonstrates how historical price information and technical indicators can be combined with a machine learning framework to model Ethereum prices. However, these results should be interpreted as performance on the historical test period used in this study rather than as a guarantee of future investment performance. So, coming to the future research and final thoughts, there are several opportunities to extend this research in the future. First, in addition, additional information could be incorporated beyond historical market and technical data. For example, real time market sentiment from financial news or social media could help capture investor behavior. So, another direction would be to compare the current machine learning models with more advanced deep learning and attention based techniques, particularly for sequential time series modeling. It would also be valuable to evaluate these approaches across different cryptocurrencies and different market periods to examine whether the performance remains consistent. To conclude, this research demonstrates the potential of combining machine learning with technical indicators for price prediction modeling. Within the models and test period evaluated in the study, ElasticNet with degree 2 polynomial features produced the most accurate predictions. Thank you.